Alright, well hopefully this won't throw any of you off. I'm doing this one outside since it's a nice cool morning. And I'm tired of sitting in a house talking to myself. So I'm just going to talk to myself on the front porch and hopefully my neighbors will think I'm totally crazy. But we're doing chapter 11 today, which is fluid statics. Great picture of a swimmer here. Swimming was my sport in high school, so I'm particularly fond of the sport. And of course, it's done in fluids. Not many sports that are done in fluids. If you ever want to see a fun sport that's action-packed and just a little bit violent, watch water polo. Of course, you can't see most of the violence. Most of the violence happens under the water. But in this chapter, we're going to be learning about everything from the very basics of fluids all the way up to the more complicated things that are considered the dynamics of fluids. Even we're going to be getting close to the dynamics when we start talking about pressures. Because pressure is related to force. So we're again going back to Newton a little bit when we get into pressures. 9 sections in here and a lot of new stuff to cover, building on all the stuff that we know so far, but still new stuff. So first of all, what is a fluid? We talk about the 3 states of matter. You've probably seen this before, where when you talk about solids, you talk about very strong bonds that are usually much more organized, often in crystalline structures, not always, but often in crystalline structures or amorphous kind of structures. The crystalline structure is generally very, very organized. Like this here, we have these squares, and if you expand them in 3 dimensions, you'd have maybe cubes or other shapes coming off of it. You can have triangles, you can have all kinds of things. Liquids are generally less bonded, much less bonded, where the atoms or the molecules in making up the liquid, they interact with each other and they have bonds that hold each other together, but they're not strong enough for the liquid to hold its own shape. It has to be in a container of some kind to have a shape, and so the liquid, the bonds can break fairly easily, and do that by boiling water or just pouring it out on the street and watching it spread out and evaporate. That's a liquid. That's the idea of the liquids at the atomic or molecular level. And then gases, of course, are essentially just free atoms or free molecules that do not interact with each other hardly at all, if at all. They're spaced out dramatically, and this does not show it anywhere near to scale, but solids and liquids are pretty much the same in their spacing of atoms or molecules, and gases are far spaced out. If this was to scale, you might see 1 particle here instead of the 5 or whatever it's got here, 6. It's very, very spread out compared to the liquids and gases. Or sorry, to liquids and solids. These are not the only states of matter. There are other states of matter. There's the plasma state of matter, where each of these atoms or molecules gets superheated and starts to lose electrons, so they all become charged. In that case, the gas not only exhibits gaseous properties, but also dynamic properties. So the molecules repel each other, in other words. And things that are plasmas include things like fire and flame. But on the other end of the spectrum, down here at the solid end of the spectrum, there are other states of matter as well. One of them is recently discovered in the past 20 some odd years, the Bose-Einstein condensate, which happens when you take a gas and you cool it down to near absolute zero. The atoms essentially collapse and become as if they were one. They behave as if they were one. They all become very close. They get very, very close together and very, very dense. And it's an interesting state of matter that was predicted by 2 scientists, Einstein, of course, whom you've heard of, and then Bose, who's an Indian scientist, I believe, who ended up working as a professor at MIT in the early 20th century, mid-20th century. But anyway, good science going on there. So that is kind of a look at solids, liquids, and gases at the atomic and molecular level. This, of course, is going to affect their density. And what is density? We're going to have to define that, because it's going to become quite important as we study solids, liquids, and gases. Density is defined as the mass of a something divided by the volume of that something, right? Very simple. Uh, it's got units of kilograms per meter cubed, and so it's not a big deal to figure out. Here they give us some densities of different substances, solids, aluminum at 2.7, up here to tungsten at 19.3, right? Tungsten is almost 10 times as dense as aluminum, and uranium is just a little bit less dense than tungsten. Uranium, of course, the stuff that they make nuclear bombs out of and they use in nuclear power plants. And then you can see ice here at 0.917, and this is actually in kilograms per meter cubed. But if we go over here, water is about 1. So this is why ice floats in water, because for a particular volume of ice, if you take 1 gram of ice, for example, it will have a density of 0.917. But if you take a gram of water and drop the ice in there, it will have a density of 1. So it actually weighs more, and the ice will float to the top. We're going to learn how that happens, why that happens. And if you've ever seen blood in water, you'll know that it sinks. And seawater is more dense than regular water. Mercury is very dense. It's almost as dense. I mean, it's way up here like lead. It's more dense than lead, and it's a heavy metal, it's the only element in the periodic table, the only metallic element in the periodic table that is liquid at room temperatures and normal pressures. Can it be solid? Yes, it can be solid. It has to be at very different temperature and pressure to be so. But mercury is an interesting and useful metal because of its liquid state at normal temperatures and pressures. We'll learn more about that. Ethyl alcohol, you can see, is lighter, less dense rather. Gasoline also less dense. This is why oil floats on water, or petroleum floats on water. Glycerin more dense. And over here we can see the gases. You can see that you have 1 kilogram. This is 1 times 10 to the kilogram per meter cubed. So it's 1,000, or it's 1 gram per milliliter. But air is 1.29 times 10 to the minus 3. It's 1,000 times less dense. So there's just not really a way to talk about the comparison of densities between. It's 1,000 times difference. It's so much different. You can't really draw that in a picture, because you'd have to have a picture that could hold 1,000 little dots for the liquid and 1 dot for the gas. It's so much less. There's so much less density in the gas. It's so much more spread out. And of course, the amount that things spread out really plays a huge role in how dense something is. Here they show a ton of feathers and a ton of bricks. Same mass, but a very, very different density. And excuse me. There are lots of examples of this. So here we're going to calculate the mass of a reservoir from its volume. A reservoir has a surface area of 50 kilometers squared and an average depth of 40 meters. So if you have the surface area and the average depth, just multiply those two together and you can get the volume. They want to know the mass of water that is held behind the dam in the Three Gorges Dam on the Yangtze River in central China. So density is equal to mass over volume, right here in this first equation. What we have is the volume. And we also have the density, because it's a freshwater lake, so we can calculate the mass. We rearrange that and calculate the mass. To calculate the volume, we just do the density cross-sectional area, or the surface area, times the height, or the depth. Then to calculate the mass, we use the density times the volume, and we're good to go. 2 times 10 to the 12 kilograms of water. That's a lot. Here is the Three Gorges Dam in central China. The world's largest hydroelectric plant in 2008. It flooded a lot of China. Made a big lake that flooded an entire city that they had to abandon and start a new city. So anyway, Over 1 million people displaced. So pressure, what is pressure? Pressure is actually a defined quantity. So we define it as the force that is exerted across an area. So it's like a force that's spread out. Instead of acting at a single point, it's spread out over an entire area, the area A. And so it's going to have units of newtons per meter squared, which we call the Pascal, naming it for a scientist, of course, who did lots of studies with pressure. And there are other units of measure for pressure. For example, there's the millibar, which is equal, 1 millibar is equal to 1 times 10 to the 5th Pascal. So you can see here that a Pascal is actually a fairly small amount of pressure. In the United States, we still use a lot PSI, which is pounds per square inch. Pounds, of course, is a force. Square inches, of course, is an area. So that's very valid. We also still use millimeters of mercury, and the reason we use millimeters of mercury is not quite so obvious, but we'll learn about it in just a second. And the idea of pressure is kind of interesting because of this inverse relationship with the cross-sectional area, or with the area that the force is being applied to. And this picture gives us a good example of how that is so interesting. If you press on someone's arm with your finger, you have a force that you're applying with your finger, but the force is spread out over the large area of the end of your finger. It's a fairly large area, and so it doesn't really do anything to the body. Just you can feel it, but not a big deal, and if you poke really hard, it might even hurt. But if you apply the same amount of force over a very much smaller area, like a needle, that needle will actually have enough pressure to puncture your skin. And of course, those two things are very different, being poked and being punctured. This is the reason that blades are sharp. Blades are sharp because you reduce that area on the edge of the blade, and then you don't have to push so hard to separate things with a knife. For example, knives are used to cut meat and vegetables and other things like this. The sharper the knife, the better. In fact, different knives are designed for different things. When you're cutting meat, you need to have a knife that is sharp but also fairly strong, because you might come in contact with a bone or with something that could harm the edge of the knife. So the edge of the knife can't be too small of an area. So they're generally thicker knives for cutting things like red meat and bird meat and stuff like that has big bones in it that you might cut through. However, when you're cutting vegetables or seafood, use a very different kind of knife. Usually the blade is much thinner because it doesn't need to be nearly so strong. In fact, most blades that you cut fish with, you can bend. They're actually very flexible, called fillet knives. And you can actually see the influence of this idea in the different cultures that make these knives. In Europe, Europeans are generally more accustomed to eating big animals with lots of bones, large bones, and so the knives in their cooking industry, European cooking knives, are generally thicker blades and not nearly so sharp, because if they were too sharp, the blade would be too thin and would crack, break, and chip on the end. However, in Asia, particularly in Japan, their knives for cooking came from a much different tradition, where they eat a lot of fish and a lot of vegetables, and so they need to cut things with a very sharp blade that doesn't need to be nearly so strong, because it's not going to encounter big heavy bones very often. And so their blades are much thinner, much sharper, and being somebody who loves cooking and is kind of enthusiastic about it, I have some of each for doing different tasks. So let's do the calculating the force exerted by air. We have an astronaut working outside the International Space Station. Atmospheric pressure is essentially zero. Why is atmospheric pressure outside the station essentially zero? Well, we'll learn about this later, but I'll give you a hint now. What exerts pressure on something that is in air? Well, it's the air. If there's no air, you can't exert pressure on something like that. There's nothing to push on the outside of the space station, so it's a zero pressure on the outside. On the inside of the space station, that is not so. There is air on the inside, so there is pressure pushing outward from the inside out on the space station. Anyway, we have a pressure gauge on an air tank on this astronaut. It reads 6.9 times 10 to the 6 pascals. And want to know what force does the air inside the tank exert on the flat end of the cylindrical tank, a disc 0.150 meters in diameter. So they've given us an area, they've given us a pressure, they want to know the force. Well, that should be easy enough. Oops. I accidentally skipped forward an entire chapter here. So pressure equals force divided by area, and we're going to go ahead and solve that for force. So force is going to equal pressure times area, and we just plug in the pressure in the area they've given us. The area, of course, is given as a radius, so we need to square it and multiply by pi, which they do here, and we get 1.22 times 10 to the 5th newtons. A fair amount of pressure inside those tanks, but still, remember that pascals are not a huge measurement of pressure. 1.22 times 10 to the 5th newtons. Well, sorry, I'm not in pascals. That's newtons. That is a big force for newtons. That's, a couple hundred pounds of pressure, at least a few hundred pounds of pressure. Might even be a bit higher than that, actually. Anyway, yeah, I was thinking pressure and calculating force. Sorry about that. Confusing myself and you guys. Well, let's look at how pressure works inside of a car tire. Excuse me. As you fill the tire with air and fill it more and more and more with air, more air will mean more pressure, because if you have more air pushing on things, of course that's more force pushing on things. More force pushing on the area of the tire gives you more force per area, more pressure, right? You actually get force. The force spreads itself out over all the areas so that the pressure will be equal everywhere. And that turns out to be a principle called Pascal's principle. We'll learn about here in a second. And we're learning about right now, I guess. It even goes up into the stem, and that's very helpful because the stem is actually closed by the pressure inside of the tire in part. There is a spring in there, but it's not just the spring that holds it closed. It's actually the pressure that holds this valve closed from inside. And this is useful because not only does it apply a pressure downwards on the ground, which you want to keep the car off the ground, but it also keeps the tire inflated. It keeps the tire, holds its shape, in other words. That's how balloons hold their shape as well. The same thing happens on pressures that are acting inside out, except in the case of a swimmer, it's slightly different because the bottom part of the swimmer is actually lower than the top part of the swimmer, and they will get you will get more pressure down here because if you're further down, you have more water pressing on you. And some people think that's because water gets more dense as you go deeper. It's not actually true. What's actually happening is that the pressure from the top of the water all the way down is the pressure that is exerted on you. So it depends on how deep you are, because this water down here has more water stacked up on top of it that is pressing on it. And so you get more pressure underneath the swimmer than above. It helps you stay afloat just a little bit. Just for, argument's sake, I wouldn't recommend trying the crawl stroke underwater. It's very inefficient. So let's talk about how the pressure changes as you go deeper in a fluid and why. And like I said, it's dependent on the depth, because the pressure of a fluid at the bottom is affected by the pressure above it, by weight, essentially. You have all this fluid above the fluid at the bottom of the fluid that is pressing downward at that bottom fluid, and that forces that bottom fluid to press harder on things around it. So it's just like having a weight on your shoulders, right? Deeper you are, the more you're going to feel. And so it turns out that it is directly related to the weight of the water above it, which is m times g, mass of the water above times g, divided by the cross-sectional area of the fluid. And so that's a new definition for force, where the force has been turned into a weight. And then if we have all these other, we have this definition for the definition for density here we're going to use, because mass is equal to the density of the fluid times volume of the fluid. Volume is equal to the cross-sectional area times the height. Mass then is equal to density times area times height. And we plug that into the equation above, and we get density times area times height times gravity divided by area. Well, the areas are the same, so you cancel them out. And it turns out that the pressure in a particular depth below a fluid is equal to h, the depth, times the density of the fluid times gravity. It turns out it doesn't care about the mass of the fluid. It doesn't care about the cross-sectional area. All it really cares about is the height, the density, and the gravitational constant. So that makes it quite simple. So to do an example here, we're going to calculate the mass of a large reservoir. We calculated the mass of a large reservoir before, but now we're going to consider the pressure acting on the dam retaining the water. It's going to be 500 meters wide, 80 meters deep. We want to know what the average pressure on the dam is for part A, and then we want to calculate the force against the dam with the weight of the water in the dam that we found already. So pressure first. Average pressure is going to equal average height times the density of the water times gravity. So that's all numbers they've given us. We go ahead and we throw them in. And it turns out to give us 392 kilopascal. And so that's the average force exerted on the average pressure exerted on the dam across the entire dam. Remember that pressure is a force per unit area. So this is the same as 392 kilonewtons per meter squared. So it's a fair amount of force per meter squared. And then the force exerted on the dam by the water is the average pressure times the area of contact. We're essentially just rearranging the equation for our pressure, right? So we go ahead and plug in our pressure that we just calculated, multiply by the area, and you get 1.57 times 10 to the 10 newtons. Of force on the dam. So that's a lot of force over the entire dam. It's the total amount of force being exerted. How is that different from the weight? 1.96 times 10 to the 13. The weight is actually much bigger than the actual force on the dam. Why is that? Well, because a lot of the weight of the water is not affecting the dam directly. It's being pressed into the bottom of the lake, right? So the only way that the weight of the water affects the dam is by the weights, is how the weight affects the pressure. So in this picture they show us a kind of a normal kind of dam. They have the forces that are being applied sideways because of the weight of all this water, and those sideways forces are the pressure that are related to the pressure that's going to be exerted on the dam here. Take that force, take the total force on the dam, and divide it by the area of the dam. You get the pressure across the dam. But this is actually the reason that dams are shaped the way they are. They're usually shaped either in a trapezoidal form here, where you have this thick bottom of the dam and a thinner top of the dam, or they are a shape that is more like a parabola or a hyperbola, where it's thin at the top and it curves down to the bottom to be much, much wider at the bottom. And the reason is because as you go deeper and deeper and deeper in the water, the force becomes much bigger and much bigger and much bigger, or the pressure becomes much bigger, much bigger, much bigger. And you see that with lots and lots of different dams. My favorite being Hoover Dam, probably. If you've never seen Hoover Dam, I'll show you a picture. Also, if you've never seen Hoover Dam, you ought to go on a dam vacation and take the dam tour of the Hoover Dam. Gotta love the dam jokes. But this is Hoover Dam. It holds back Lake Mead, which is a big source of water for Arizona and Southern California. It says Arizona, Nevada, New Mexico, and California. Anyway, it holds back this big lake, and you can see that the lake is receding. This white area on the rock is actually, let's see if we can get a better view of this. Here it is. This white area on the rock is where the water used to be at, and it's down low now. And they're, they've been having drought for a while. They'll get it back though eventually. They should get back some of that, actually quite a bit of that water this year because of all the rain. This dam is fed by the Colorado River, which is getting a fair amount of water this year. This is what the dam used to look like. It doesn't look like this anymore quite. You used to be able to drive right across the dam. You'd go over the dam on this road here that you can see, but this is a picture taken quite a while ago. Now, the dam, and this will always kind of, these leaning towers always kind of concern people. They have these power lines that go across this gorge here, which is just kind of crazy. At the bottom here, you have the power plant. This is where the big generators are that turn as water goes through the dam. There's water coming out down here, and when this thing is letting out as much water as it can, when they've got really high water in Lake Mead, it's just, there's these, you can't really see them from here, but there's these huge spouts further down, these huge holes that let water out, and they spray for hundreds of yards, or huge spouts of water. But all this down here is where the generators are. The turbines are in here that turn. They turn the generators, and then they have all these electrical buildings down here that convert the electricity into the proper voltage and current and send it out to the southwestern United States. Because of terrorist threats, they've decided to stop traffic across this dam. Of course, if a terrorist ever got on this dam and put a big bomb on it and caused serious damage, when water spilled over the top of this or through this dam, lots of towns and cities downriver would be in danger, because this is a very big lake up here, and a lot of water, a lot of volume water. So what they did is they closed this road, and they actually put a bridge across here. So now there's a bridge here. I wonder if we can see that on one of the other pictures. Let's check it here. Yeah, here's the new bridge. So now they've closed the road. Whoa. Oh. Hey, there's those generators inside. Those aren't the turbines, but those are the generators. Where'd the picture go of the... Anyway, you can see that there's a bridge there now. Now we got some police coming nearby here. They're asking questions like, how long will this Hoover Dam last? Because Hoover Dam's been there since the 20s or 30s is when they started. It's named after President Hoover, who was president during Depression era. He was the president before Roosevelt, who came in and led us into World War II. And here is Hoover Dam with the new bridge across there. And you can also kind of see that the lake is much higher in this picture. So, anyway. So, getting back to business here. Oh, another measure of pressure, another unit of pressure that we use quite a bit are called atmospheres. One atmosphere is essentially the pressure that we feel on an average day in the world outside. It's about 1.01 times 10 to the 5th pascals. And that's kind of a normal pressure day on planet Earth. We often call that 760 millimeters of mercury, or 29 inches of mercury as well, for reasons that we will explain soon. And where does the pressure from the air outside come from? Well, simply put, when you're on the surface of the Earth, it's like you're immersed in a pool of liquid, or not a pool of liquid, but a pool of fluid. And the fluid is the air on the Earth, which is mostly made of nitrogen, and it's very, very tall. If you took a 1 meter squared area on the Earth right here, which is what they're doing, and you extended that area upward until you got to the outer reaches of the atmosphere, the weight of that big square-shaped cylinder of air would be equal to 1.01 times 10 to the fifth newtons. And so that's the amount of pressure. You say, that's a lot of weight. It is a lot of weight. Several hundred pounds of pressure, of several hundred pounds rather, of force on top of your head. How do we withstand it? Well, human beings were built for this earth, you know. However you want to think about it, if you are a believer in the more scientific view and you believe in evolution, the human body evolved in this pressure, and so the skeletal system and the muscular system and the circulation system were all being created by nature in this way. If you believe in creationism, we were just built to be on this earth. So either way, we were created to withstand these kinds of pressures. We were not, however, created to withstand the kinds of pressures on other types of planets, either less pressure or more pressure. Our bodies don't do well in either. If you put less pressure on our bodies, we actually begin to have bleeding from the inside out, because there's too much pressure inside of our cells for having less pressure outside of our body. So we call that edema. If you go climbing up on Mount Everest, every human being that climbs on Mount Everest, except for one race of people, gets edema fairly rapidly and begin to die from the inside out. They begin to bleed from the inside out. The only race that doesn't are the people that actually live there. They're called the Sherpa people, and they live in the Himalayas, and most of their towns are well above 15,000 feet, and it's usually above 15,000 feet that most human beings begin to struggle. What happens really, it happens first usually in your lungs, and the blood vessels in your lungs start to burst because there's too much pressure inside the vessels and not enough pressure outside to hold the blood in. And so they start to burst and you get bleeding from your lungs, you start coughing up blood, and it can become much more severe. This is why when you go to climb mountains in the Himalayas and other mountains that are that high, there aren't very many, but most of them are in the Himalayas, but some are in South America. And there's even one in Alaska. But when you go climb mountains that are over 15,000 feet and up in the 20,000 feet range, up to 30,000 feet where Mount Everest is, you have to do it quickly. It's really a race against nature. It's a race against your own death. You have to climb the mountain before you die. And then when you get down, you have to recover. It's not a pleasant thing. Mountain climbing is another sport that I was into a lot when I was young. I kind of gave it up when I got married and came to Nebraska because there's no mountains in Nebraska. But I'm hoping to try to take it up a little bit here, travel to Colorado and Wyoming, do some mountain climbing again. So let's calculate average density. How dense is air? Density is defined as mass per volume, but from our equation for pressure and density, we have pressure equals height times density times gravity, so we can solve that for density if we know the height of the atmosphere, which we can get, turns out to be about 120 kilometers high. And so we go ahead and plug that into our equation with the with the pressure of one atmosphere, 1.01 times 10 to the fifth Newton per meter squared, and the G, and we get 8.59 times 10 to the minus 2 kilograms per meter cubed for the average density of air on the Earth. So it's the average density of the Earth's atmosphere is quite a bit less than actually the density at where we breathe, since this is an average. At the top of the atmosphere it's much less dense, and at the bottom it's much more dense because air is compressible as opposed to water. But that is an average. Here in this example we're going to calculate the depth below the surface of the water. What depth of water creates the same pressure as the entire atmosphere? So how far would we have to go underwater to feel the pressure that we feel on the Earth? This is kind of a trick question because right at the surface of the water, the surface of any body of water on Earth has the pressure of the entire atmosphere on it. And so you have to add the pressure of the atmosphere to most pressures that you feel underwater. But we're going to do underwater with no pressure above it, I assume. And so pressure equals H times P times G again, and we're going to calculate the H from the pressure. We plug in our numbers and we get 10.3 meters. So if you go under 10.3 meters of liquid water, that has no air above it to press down on it. So it's just feeling the pressure. You're just feeling the pressure from the water. You have to go 10 meters. And most people have never been 5 meters, let alone 10 meters underwater. 5 meters, of course, is nearly 20 feet. 6 meters is 20 feet. And 10 meters is 35 feet. That is significant depth, and most people cannot swim below 20 feet without having severe headaches. Why do you get a headache? Well, you get a headache because the pressure inside your eardrums is normalized at 1 atmosphere. Essentially, the pressure inside your ears is 1.1 times 10 to the 5, and the pressure outside of your ears is 1.01 times 10 to the 5. And that's normal when you're walking around doing what you do, right? When you get 10 meters underwater, you have that much pressure from the water, but you also have that much pressure from the air above the water. And so it's twice as much pressure on the outside of your ears as on the inside. And that really pushes on your eardrums, and your eardrums have nerves, and it makes your eardrums hurt. And of course, the pressure inside of your head will increase as your eardrums get pressed inward, and so you have increased pressure of fluid inside your head, which really hurts. And people who dive have to equalize that pressure. How do they equalize that pressure? Well, use the natural instinct of your body, which is to yawn. Yawning is what your body does to equalize pressure in your ears. Generally, when you go to sleep at night, the pressure in your head, the pressure in your eardrums changes slightly because there's not very much noise when you're sleeping at night, and your ears can relax a little bit. And when you get up in the morning and you yawn, you're equalizing those pressures. When you're getting tired during the day, very similar thing is happening. Your ears are used to hearing lots of things, or feeling lots of pressure from the sounds around you all day long, and then your ears begin to relax, and the pressure differential between the outside and the inside starts to change, and your body wants to yawn to fix that. It's the same reason you want to yawn when you're in a plane, because when you're going in a plane up and up and up and up, you're getting less and less and less pressure on the outside of your ears. The inside of your ear, the fluid on the inside of your ears is pressing outward. You yawn to equalize that to make it better. Most people struggle with yawning underwater, but divers have to get used to that. Swimmers have to get used to that. You have to get used to yawning underwater. Yawn without opening your mouth, for example, or if you do open your mouth, let the water in, just don't breathe it. And you can equalize yourself. And they also do things like holding their nose and blowing bubbles, and there's other tricks for it. But you can equalize down to 35 feet pretty easily. In fact, you can go down quite a bit deeper, probably about twice as deep, without having any kind of equipment to help you out. If you go much deeper than that, then you actually have to have special equipment for going deeper. You can equalize your ears, but you can't equalize your lungs so easily going below about 50, 60 feet because at those pressures, the air in your lungs will actually begin to, sorry, not the air in your lungs, but the oxygen in your blood will actually begin to boil out, it'll start to evaporate essentially. And when that happens in your blood, you get oxygen deprivation essentially. The oxygen leaves your blood, so you don't have any oxygen there. And in that case, when that happens in your brain, you get what's called the bends, and it makes you feel woozy. You can pass out, and of course, passing out 60 feet underwater, not a good idea. And that usually happens when you have a rapid change in pressure, when you go down deep and then you come up quickly. Your body can adjust to those things, but it has to be gradual, and you have to start breathing different pressure of air to make sure it doesn't expand in your blood. And so if you can increase the pressure of air that you're breathing, you can do just fine at very deep depths. In fact, drilling rigs that go down hundreds and even thousands of feet underwater are designed so that the divers spend maybe as much as a day going down, getting used to the pressure, slowly increasing the pressure of the air in their lungs, slowly increasing the pressure of the fluid in their ears, and then once they get used to it, they can actually free dive. They don't even need tanks or anything. It's not fun because it's freezing cold water, but it's always best to seal everything up and be good to go. But you can actually hold your breath just fine down there, even though the pressures are very extreme, and your body can handle those pressures. Your body's actually better at handling high pressures than low pressures because you don't have edema problems, you don't have internal bleeding problems when you have very high pressures. the blood in your body stays where it is because of those extreme high pressures outside. So, I mentioned this one before, Pascal's principle, this idea that pressure spreads itself out in a fluid. And that is true as long as the fluid is pretty much all at the same depth, not very much depth change in the fluid. A few feet of depth change is not going to make a huge difference, whereas, tens of feet and hundreds of feet of depth makes a big difference. But Pascal's principle says that if you change the pressure that has been spread out nice and evenly inside of one of these, inside of a container holding a fluid, that the change in pressure will transmit itself to all of the fluid and all the walls of the container. Now this is assuming that you have an enclosed container and the container is completely filled with one kind of fluid. There's not multiple different fluids going on in there. But if you have an enclosed fluid, that change in pressure, if you apply a pressure to one side of the fluid, that pressure will transmit itself throughout the fluid. So if you go from 10 to 20 on one side, everything goes up to 20. This turns out to be an important principle in our everyday world. And this is the reason. This is a very simple pressure system where we have a small container over here and a bigger container over here, and they're connected, and they're all about the same height in fluid. So Pascal's principle should apply here, and these two green things are movable pistons. They're essentially a surface that is part of the container, but it can slide up and down in the container. And so you can apply a force to this one over here, this smaller one over here, and it will squeeze the fluid and apply a pressure on the fluid. And then that pressure will transmit itself through this little connector into the bigger tank, and it will apply a force or a pressure on the bottom of this other cylinder, and that force will be exerted up on the other side. But notice that force 2's arrow is much bigger than force 1's. And the reason for that is due to Pascal's principle. Pressure 1 and pressure 2 are exactly the same because of Pascal's principle. However, area 1 is much smaller than area 2, and if the pressures are going to be the same, but the areas are different, then you get this idea where the pressure has to be bigger to make up for that area difference. So you have pressure equals force divided by area, right? And if the force gets bigger on the top of that fraction, then the area has to get bigger on the bottom of the fraction to keep it the same number, to keep it the same pressure, in other words. I'm actually going to go to Educreations really quick and show that as a little, I'm going to show a little math of that because it just makes sense. Let's go back here. Where do we go to the create here? Lessons. Where's the create a lesson? Class lessons. Where's the create a lesson button? I can't find. Oh, there it is. Create a new lesson. So the way that this goes is that the pressure is equal to the force over the area and if this is the first pressure that we apply, it's equal to the first force over the first area. But of course that first pressure is equal to the second pressure, and the second pressure is equal to force 2 over area 2. Right? The problem is that area 2 is huge compared to area 1, so it's this big A instead of a little a. In order to make these two things equal, we have to have a big force to make up for it. It's kind of funny. So little force over little area equals big force over big area. Well, now how can we take advantage of that? How can we make use of that in the real world? It's really quite simple. This is the system that stops your car. Guess which one is the brake pedal? Well, the brake pedal is the place where you exert the small amount of force. You can exert a small amount of force with your foot on the brake pedal, and it pushes a small piston and provides a pressure in the fluid system of your braking system. Your braking system has what's called braking fluid, which is essentially oil in it, and the oil, it feels this pressure, and that pressure spreads itself out through the entire oil system. There's some little tubes that go from the brake pedal back to your brakes or forward to your brakes, or whatever. And this is what we call the master cylinder. And then these brake cylinders out here are bigger, much bigger in area, and there's more of them as well, and so that makes a difference in the area too. Because most cars have 2 to 4 of these on each wheel, of each of these cylinders on each wheel, usually 4 on each wheel. And when you exert that pressure outward like this on this upward on this other bigger cylinder or bigger piston, then of course that force has to be bigger, and because the area is bigger, and with a bigger force you can connect this piston to the brake pads, and the brake pads press up against the brake discs and stop the car. This is what we call hydraulics. It's called hydraulics because it is taking advantage of hydrodynamic, it's really hydrostatics, but it's taking advantage of hydrostatic forces and pressures. So it's a hydraulic system. So here we're actually going to do an example of this. So the master cylinder is the one that we press on here with our brake pedal, and then these other ones, the brake cylinders, are also called slave cylinders, and they are going to exert forces. These are drum brakes, and so you have these shoes, they call these shoes, on each side here, and you have this cylinder in between, which is called the slave brake cylinder, and the fluid comes in here, and it has 2 pistons on it. One piston that pushes forward, one pushes backwards, excuse me, and it pushes the shoe into the wall of the brake drum. This brake drum is like a big, it's kind of like a drum, and so the brake shoes press up against the side of the drum. This isn't very well drawn because the brake drum is usually made of a thick piece of steel to handle all the friction and the heat that's going to be applied to it. But then you have another one here for the other wheel, and you've got brakes. And generally you'll have 4 of these, one on each wheel. But in this problem, they say we're considering this system. So they have 100 newtons on the brake pedal, and the brake pedal itself actually increases the force because it's a lever arm, and so you get some torque things going on, and you get more force even at the master cylinder. And so we're going to calculate these things. Turns out that you get 100 newtons applied to the brake pedal. You get 500 newtons exerted on the master cylinder, and you can use statics and torques and everything to figure that out if you want to. And then the pressure created in the master cylinder is transmitted to 4 so-called slave cylinders, or 4 brake cylinders. Master cylinder has a diameter of 0.5. Slave cylinder has a diameter of 2.5. We have to convert those into radiuses so we can square them for areas eventually. Then essentially we're just using the equation force 1 over area 1 equals force 2 over area 2. Then we're going to solve for force 2. Solve that equation for force 2 and you get area 2 over area 1 equals force 1, or times force 1 equals force 2. And we just plug in our numbers. Half of the second area rather squared divided by half of the first area squared, and we can leave it in centimeters if we want to because the centimeters are just going to cancel. Multiply that by the 500 newtons of force that we are going to apply, and it turns out we get 1.25 times 10 to the 4 newtons of force. So we put in 500 newtons and we get out 12,000 newtons. So that's a good deal. That's exactly what we want to do. That's how we want to make brakes work. Okay, I'm going to take a little bit of a break here. I'm going to go get a drink, blow my nose. And we're going to come back and we're going to talk about now gauge pressure, absolute pressure, and pressure measurement, which is where we're going to learn about millimeters of mercury and inches of mercury and things that I've talked about that we haven't explained yet. So I will get back to you in just a few minutes. Okay, we're back at it. Gauge pressure, absolute pressure, and pressure measurement. How do we measure pressure? And particularly, we're going to be looking at how we measure pressure in systems and how we measure pressure just out there in the world. And how do we measure air pressure on a given day? We all see it on the news when we're watching the weather. How do we measure those things? And so first of all, we have to define what we're actually measuring, because with pressure, it's a bit tricky. First of all, we'll start with gauge pressure. Gauge pressure is a relative measurement. It is not an absolute measurement. What do I mean by a relative measurement? Well, if we go to some of the things that we've talked about before, for example, speed. Speed is a relative measurement relative to how fast the person who's measuring the speed is going. So we're on the Earth, and we're spinning around in circles on the Earth, and the Earth is winging through the solar system. The solar system is spinning around the galaxy, and all those movements are movements that we don't take into account when we measure the velocity of a car. And so when we measure the velocity of a car, we're actually taking a gauge measurement of that car's velocity, which means we're measuring the velocity relative to our velocity that we're kind of ignoring, right? Gauge pressure is a very similar kind of measurement, where we're going to measure the pressure of something relative to the pressure that is outside, relative to the pressure that we deal with normally. So for example, tire pressure is that kind of a pressure measurement, where we're measuring how much more pressure the tires have compared to the pressure outside of the tire, because that's what we're really interested in. We want the pressure in our tires to be 35 pounds per square inch more than the pressure outside, so that they will withstand the forces that are going to be exerted on them from the weight of the car and from turning corners and everything else, and also the air on the outside of the tire, which is pressing on the tires as well. So that is a gauge measurement. I mentioned that one because I just took my car in, which is an old beat-up Chevy truck, and my kids' car. My three older kids bought a neighbor's car. It's a 1989 Custom Cruiser, which is a super long station wagon with fake wood stickers on the side. It's pretty sweet. It has spoked wheels and a backwards-facing seat in the back. But anyway, I just took those two cars in to get them oil changed and everything else, and they checked the tires, and they inflated my tires to a gauge pressure of 35 pounds per square inch. And this is different than other types of pressure measurement. For example, absolute pressure. Absolute pressure is measuring the pressure relative to zero pressure. Zero pressure means there is absolutely no force being applied across the particular area you're interested in. And that's a very different kind of a measurement. So how are we going to measure gauge pressure? How are we going to measure absolute pressure? And how are we going to relate the two? Well, it turns out that since gauge pressure is related to atmospheric pressure, in other words, it is compared to it, we can actually make an equation which they put right here. Absolute pressure is always going to equal the gauge pressure plus the atmospheric pressure. You add on whatever pressure you're comparing it to, and that will give you your absolute pressure, the total pressure involved. So that is just a simple equation, and then we can actually solve these things we can solve these ideas for different situations. For example, if our gauge pressure is zero, then if we call our absolute pressure zero, if we say we're at absolute zero pressure, if we have no pressure, this equation becomes 0 equals Pg plus P8 atmosphere. And then you can solve it for Pg equals negative P atmosphere, right? And this is actually the beginning of starting to understand what pressure is all about, and how low pressure can get, and how high pressure can get, or whatever else. Here is a very simple machine for measuring gauge pressure, and actually they're called pressure gauges for measuring gauge pressure. And this pressure gauge works on a principle of force essentially exerted over a particular area. So here's what we have in here is this bellows that flexes, and this bellows is connected to an outside tube kind of thing, where the pressure from the outside can enter the tube and press on the bellows. So that's the pressure being measured. As this bellows gets pushed inward or pulled outward, depending on pushed inward for high pressures, not pushed inward as much for lower pressures, it is connected to this little lever arm that has a pivot, which is connected to a spring, and the spring has a particular spring constant. So you can calibrate this thing. You calibrate it by putting this thing outside on a normal day when you have normal pressure, and then making this arrow point to the normal pressure on the scale, which normal pressure would be 1.01 times 10 to the fifth if it was in pascals. But it might be something else if you were using different units of measure. And so that's how you use, that is one, a bellows type, or there's other names for it as well. But it's essentially an aneroid gauge, they call it, of pressure gauge. But there are other types of things that measure pressure. Here we have what is called a manometer. We have a closed tube manometer and an open tube manometer. The open tube manometer is open to atmosphere on both sides. Actually, they're both called open tube manometers now that I think about it. Yeah. Anyway, these are called manometers, and the manometer is a tube that's U-shaped and has a ruler down the center. And when both tubes are open to the atmosphere, this liquid that they pour inside the tube is going to have the same height on both sides because it's being pressed on by the same pressure on both sides. However, if you connect it to something like this balloon shaped like Mickey Mouse's head, and then you put some pressure in that balloon, then the pressure on the side of the balloon is going to be more than the pressure on the other side. They used to be equal. We added some pressure on this side, and now it's more on this side, and it pushes the liquid down on the side of the balloon, which makes the liquid raise up on the other side, and now there's a difference in height. Well, of course, we have an equation that tells us something about the difference in height and difference in pressure. Remember, the pressure is equal to H times P, or H times rho times G, where rho is the density. And if that's the pressure difference, then the absolute pressure is going to be atmosphere plus that. So you can use this to measure absolute pressure, right? Or you can use it to measure gauge pressure, and then you can use it to calculate absolute pressure. You can also use it the other way. Instead of having something with increased pressure in it, something with decreased pressure, like a bottle of food that you're trying to vacuum pack. As you're vacuum packing it and you're sucking the air out of it, there will be less and less pressure in this bottle of food, and the pressure will be less on the side with the bottle and more on this side, which means it's going to be pushed down more on the left side, open to atmosphere, and so this one will go down further, this one will come up higher.
Did you just say right one of them?
No, both. Okay, so sorry I had had to talk with my daughter there for a second. But anyway, so it can work either way. It can work for low pressures or high pressures, and you can calculate pressure using manometers. Manometers are actually used for blood pressure in blood pressure cuffs. They're in the old-fashioned blood pressure cuffs. You actually have that little thing that rises up on one side as you pump up the cuff, and that's increasing the pressure on one side of the cuff. It's kind of like this situation with the balloon, right? And this side over here is where you have the little marker that rises up, and the fluid they use is usually mercury, that liquid metal that was very dense that I was talking about, because it needs to be a fairly dense liquid to get a good measurement. If it's water, the water will just go flying out of the tube. There's so much pressure. But that's a very common place that manometers are used. But in some more modern blood pressure machines, they're actually using something similar to this. It's not actually a bellows thing here with a spring and a lever. They're actually using a computer chip version of this, the surface that feels the pressure on this end and then puts a reading out digitally. But either way, that's what's going on. So blood pressure is blood pressure essentially has a maximum end and a minimum end, right? The maximum end they call the systolic pressure. They've written these down here for me because I always forget which one is which. And then the lower end is called the diastolic pressure. And essentially, um, what they do is when they put the cuff on your arm, they pump up the cuff until your blood stops flowing, and that's the maximum pressure that your blood is putting out, the maximum amount of pressure that your blood can push through as it tries to push past that tightening cuff on your arm. And then as they release it, they start listening for your blood to flow through the arm without any kind of restriction. That's something that they can hear as they put that stethoscope up against your vein. As they put the stethoscope above up on your vein, they can hear when the blood is flowing without any restrictive sounds coming through. And the restrictive sounds, I don't really know what they sound like. I imagine they sound kind of bubbly and like turbulence or something. I don't really know what they sound like, but doctors and nurses know that, and thank goodness they do, because it's important stuff. Normal blood pressure 120 over 80, 120 being your systolic, diastolic being the other one, systolic over diastolic, and low blood pressure can be bad for you, and high blood pressure can be bad for you. Most people that suffer from blood pressure problems suffer from high blood pressure problems. And why do they suffer from high blood pressure problems? Generally because they've got stoppages in their system because they eat too many fatty foods, or they might have a problem because of overweightness. When you're overweight, your body has to work really hard to push the blood through your system, so it increases the pressure of the blood through your system. And why is that bad? As you increase the pressure in your blood, that expands your blood vessels, and it really presses on the outside of your blood vessels. Your blood vessels are kind of like muscles, and they're always trying to hold the blood in. And as you get older and older and older, they get tired, just like all of your muscles. And if they get tired from trying to hold all this blood in, they will eventually collapse. And the places that they're most likely to collapse are in those places that are clogged with things like with the things like plaque and other things that come from fatty foods, from nasty foods like pork and pork and beef are probably the two biggest culprits in the human diet for that kind of problems in your blood. Bacon and sausage and pork chops and ham, but also beef is a huge problem. Lean beef is not such a big deal, but any kind of fat in the beef, any kind of beef fat, is terrible. And so even if it's 90% lean or 98% lean, that little bit of beef fat is a problem no matter what. And so that's the real problem with beef. Well, of course, we like our beef with lots of fat. Nebraska beef has the most fat of any beef on earth, and that's why it tastes so good to people. They like the juicy flavor, and hot grease is just kind of one of those things that people like to eat. Makes the beef very tender as well. If you eat beef from other parts of the country, it's a little healthier, a little bit less fat. If you eat beef from other parts of the world, it's actually a lot healthier because most beef is actually not corn-fed. Corn-fed is essentially like injecting sugar into your cow every day. Most beef is grass-fed all over the world, and grass-fed beef doesn't get nearly the amount of fat content in it. I mean, just nowhere close. And so it becomes much leaner. Of course, that means that it's going to be much less tender. The beef that you get in Brazil or Argentina or other places like that, not nearly so tender. You're not going to just be able to cut through it like butter or anything. But it actually has also a very different flavor. Whereas the very fatty beef in Nebraska has a very I would say very bland flavor. A lot of people like that flavor, but I'm not necessarily partial to it. But Nebraska beef has a very straightforward, very simple flavor to it that people like because it doesn't introduce grassy tones or herbal tones to it. So you get a very plain flavor, which goes well with everything and is easy to season. Whereas you get, for example, there are beef cattle in the South that are fed on different grains like wheat and hops and other things like that, and then grass. They're grass fed most of their life, and then finished on different grains than corn. Give you a very different aromas in the beef. The beef becomes much. There's much more flavor. Whether or not you like that flavor is a big issue. It's like eating lamb, where lamb has a very strong flavor most Americans don't like because they're grass fed. And grass has a very different kind of flavor that comes through than corn does. Corn is pretty much flavorless. So, well, it has a very, very sweet flavor, which definitely comes through in the beef. But, um, I mean, besides the sweetness, there's not much other interesting flavors going on. Why did I go off on that tangent? I don't know, because I'm interested in food like crazy. But anyway, it is related to this because beef is such a huge part of the American diet. I mean, we eat more beef than in the entire world combined because we can. We can raise beef very easily in our country. And it actually causes huge problems with the blood pressure because we're choking off blood vessels and we're making ourselves fatter than the average person on Earth. So our blood pressures are generally quite a bit higher in the United States than they are anywhere else in the world. And this is something we're going to learn about. We will also learn about how plaque in the veins and the arteries causes, I mean, plaque usually builds up in arteries, but it doesn't really matter if it's in the arteries or the vein, it's still going to cause problems. But how that's going to cause things like strokes, and that's quite important as well. And this is the reason that medical people have to learn physics. These chapters right here are some of the most important things the because the blood system, you know, the what is that called? The blood system. They have a word for it. But anyway, circulatory system. There we go. The circulatory system of the body is so important to everything that happens in the body. The blood carries the nutrients. The blood carries the oxygen. The blood carries out the waste. The blood carries the energy. Everything. The blood carries everything throughout the body. And if that system's not working well, none of the systems will work well. And so physics becomes an extremely important part of medicine. Of course, they learn it in they learn very specific things about medical physics in their medical classes after they've taken physics. So now we're going to do another interesting medical problem, calculating the height of an IV bag. This is actually directly related to the stuff we're talking about. Height of fluid. It doesn't really matter the shape, because in an IV bag you have this big bag that has this big area across it, and then at the bottom of it you have a small tube. And the small tube is a very different shape, but it doesn't matter. Pascal's principle, Pascal's principle doesn't really apply here because it's different heights, a few feet different height, right? But it's not Pascal's principle we're interested. We're interested in this pressure at a depth, because at the top of the bag the pressure would be much lower than at the bottom of the bag. And so if we raise the bag up higher, the bottom of the bag, which is actually the tube, will be at higher pressure. And that's important, because once you put something into someone's arm, there has to be enough pressure in the fluid that you're putting into their arm that it can overcome the pressure of the fluid inside the arm or the blood. Otherwise, you don't get the fluid going from the bag into the arm, you get the fluid going from the arm into the bag. And anybody who's spent any time in a hospital knows that that happens. And it's not necessarily a very pleasant thing sometimes, but you're certainly not going to get the fluids you need. You're just going to be losing blood into the bag. The blood from your vein will go into the bag instead of the fluids from the bag going into your blood. So you got to get that bag at the right height, which is why those bag hangers are all adjustable. If they see blood going into the bag, they raise it up a little bit. So let's see here. We have the density of fluid being administered is 1 gram per milliliter, which is about like water. What height should the bag be placed? So the entry point of the fluid enters the vein with blood pressure 18 millimeters of mercury above atmospheric pressure. Well, we didn't really talk about millimeters of mercury yet, but we probably should if we're going to do this. I don't think that they gave us a conversion for millimeters of mercury yet. Well, I suppose I can talk about it here really quick. Pressure is measured using this instrument. The air, atmospheric pressure, pressure outside is measured using an instrument similar to the manometer, except that both ends are not open. So it's more like this manometer over here. But instead of having them both kind of at the same height here, they actually have one of them, the closed end one, up at a high height, and the open end at a bottom height. So it's similar but different. And in fact, it's even most like this one because they actually put a zero pressure on this end over here, a vacuum at this end. And how do they do it? Let's go see if we can find how they do this really quick before we do this example. See if we can find a picture. Oh, here's a picture. So this is how they do it. And it makes use of mercury, of course, since we're measuring millimeters of mercury. They take a tube, like just a long tube. It has to be about a meter long or so, and they fill it up with mercury. Fill it up to the very top with mercury. The tube is closed at one end, and they fill it up to the top. Here they have it showing upside down. But first they do it right side up. They fill it up to the top, so that it's got that slight bead on the top, so that there's slightly more mercury in it than it can hold, and it's just kind of holding itself in with what we call the surface tension of the mercury, right? So anyway, once you've got it all just slightly overfilled and it's just holding itself barely in the tube, then you take a tub of mercury and you put some mercury in there. You don't fill that one all the way, but you put a little bit of mercury in there. And then you turn the tube over into the tub without spilling anything and without letting any air into the mercury. It's a little bit tricky, but it can be done. And once you've done that, once you've been able to do that, then this is what will happen. Some of the mercury in the tube will come out of the tube. But since you didn't let any air into the tube, and this tube is sealed under the pool of mercury, there couldn't possibly be air in the top of the tube, but there is a open space up in the top of the tube. And it turns out that what has happened is that the weight of the mercury has pulled down through the tube and spilled some of the mercury into this tub, and it's made a vacuum up here. It's got enough weight, it's got enough force pulling down on the mercury that it actually has enough energy to create a vacuum up here. And so the pressure up there is zero. It is absolute zero. It's not a perfect zero because you're going to get a little bit of mercury gas up in here above the liquid, but it's going to be so small that it's essentially zero. But what's holding it up there? Why is it not just all spilling out? Well, it's not all spilling out because there's still pressure pressing on this liquid out here in the bowl. The atmospheric pressure from the atmosphere above the bowl is still pressing down on that, and it turns out that it's just enough pressure to hold all this mercury up in the tube. And no matter what, it doesn't matter if the tube is really wide or really thin, as long as it doesn't get super skinny, like thermometer skinny. If you keep this, at least a few millimeters wide, it's best to keep it like a centimeter or more, so that the sides of the tube, the friction with the tube is not important. If you keep this wide enough so the friction is not a big deal, then this thing at normal atmospheric pressure, this column of mercury will be 760 millimeters tall, approximately. And so that's why they talk about millimeters of mercury. So that's when they start talking about millimeters of mercury, that's what they're talking about, is how tall this is. You can also talk about that with the manometers. If your manometers are filled with mercury, if your manometer is filled with mercury, that height or that millimeters of mercury is going to be the difference here, and you can calculate the pressure, the gauge pressure, using H times the density of mercury times gravity. And so whenever we talk about millimeters of mercury, if we talk about it with a barometer, just the absolute pressure outside, you look at the barometer, which is this device. If they're talking about a difference in pressure, or a pressure related to another pressure, that's the gauge pressure, and you use the manometer height and use this equation to calculate the actual pressure, the height of the mercury times the density of the mercury times gravitational constant. So that's going into this next example. Those are the things we have to realize when they talk about millimeters of mercury. So now, when we go into this example, it says we want the blood pressure in the vein is 18 millimeters of mercury above atmospheric pressure. That is comparing one pressure to another. So that is going to be a gauge pressure. We'll use the rho times G times H for that. And they actually give us a conversion, so we don't even have to do that, which is kind of nice. Turns out that 1 millimeter of mercury is about 133 pascals. So we just take our 18 millimeters, multiply it by that conversion, and we get 2400 pascals for the pressure that we need to get so that we can have the fluid from the IV bag flowing into the vein. If it's less than 2400 pascal, the blood will flow from the vein into the bag, and we don't want that. So we want it to be more than 2400 pascal. So we're going to use our equation again for the height for gauge pressure, and we're going to plug in this gauge pressure 2400 into the pressure side, and we're going to calculate the height. So we're going to solve for height. We get height equals pressure over density times gravity, and we're going to use the density of the fluid this time that's in the bag. They give us the density of the fluid is 1 gram per milliliter. It's about like water. Then we use 9.8, and we plug those numbers in. You get 0.24 meters. So about a quarter of a meter. Turns out to be just a little bit less than a foot, I guess. Usually they're placed higher than this so that the fluid will go in more quickly. Right? If you've ever given blood, they put the bag, the collection bag below you, right? So that the blood will flow out of your arm into the bag. Okay. Now we move on to the really exciting stuff. Archimedes' principle. So if you've never heard the story of Archimedes, I'll tell you now. Everyone should hear it. It's a great story. Archimedes was a great scientist, great physicist, one of the Greek philosophers that did more than just science. Did a lot of mathematics, a lot of geometry, and he did a lot of physics. Well, one day the king of Syracuse, which was where Archimedes lived, came to Archimedes and said, I have a crown that has been made for me by the goldsmith, and I want to know if the crown is pure gold like I gave him, or if it has been mixed with some other metal like silver. Because if you mix silver with gold, you get an alloy that looks just like gold and has pretty much the same properties of gold, but it's not pure gold. It becomes what we call like 22 karat gold or 18 karat gold or 14 karat gold. The more silver you put in, the lower that carat number goes down. But 24 karat gold is pure gold, and that's what he wanted to know if his crown was made of. Well, Archimedes was tasked with figuring this out without damaging the crown. The crown didn't have any hollow parts in it. It was all solid. It was all solid metal. And so he was trying to figure it out. And as the story goes, Archimedes was taking a bath one day. And as he soaked in his bath, he put his arms from the side of the bath into the bath water and noticed something very interesting. Anybody who's ever taken a bath kind of knows that this happens. As you take your arms and put them into the water, and normally your arms, often your arms will kind of float up on top of the water a little bit. But as you force them down under the water in the bathtub actually rises up. And as the water in the bathtub rises up, you'll notice that it gets harder to press your arms down into the water. And as he thought about this idea, he realized what was going on. And he was so excited that he jumped out of his bath and he went running through the streets of Syracuse, naked and wet, yelling, Eureka, Eureka, which means I have found it in Greek. So Eureka, Eureka, running through the streets. You might every once in a while see a picture of Archimedes. In fact, we should look for a good picture of Archimedes. Archimedes. Because there's always a funny cartoon of Archimedes running through the streets. He's always got a big beard so that he stays somewhat modest. But here's some great drawings of Archimedes, and some of these are actually taken from ancient um, ancient art and other things. Here's a great picture of Archimedes. Archimedes did a lot of stuff besides this, but where is he in his bathtub? I just saw that. Well, there's a picture of him in his bathtub there. Archimedes was also the one that that figured out a lot of the science that had to do with levers, lever arms, and things. And one of his famous quotes says, "Give me a lever and a place to stand, and I'll move the world." And very, very famous quote. Um, he also figured out a way to. He also he also invented a method for burning ships that were trying to attack Syracuse. Syracuse was had a port, and this is an interesting thing here where they had the sun shining on different mirrors, and the mirrors would all be pointed at a single ship to set it on fire. That one never really worked out, but had he known just a little bit more, he would have been able to figure it out and do that. Here's another picture of him in his bathtub. Usually they have a really funny picture of him running through the streets with his long beard yelling Eureka. But anyway, he figured it out. He figured this thing out. And what was it that he figured out? He figured out that as his arms went down into the pool, they were displacing water. The water that was where his arms were now going had to go somewhere, and it had to rise up in the tub. Well, because it had to rise up in the tub, that meant that the tub water was deeper, even though there was no more water in the tub than before. That water that raised up was trying to get back down. The force of gravity was trying to pull it back down in the tub. Well, what happened to that force? What happens to that force? According to Pascal's principle, that force gets spread throughout the liquid in a form of a pressure. And that pressure exerts itself not only on the edges of the bathtub, but also on his body. And so his arm was feeling more force on all sides, including the bottom, pushing it back up. And because the bottom of his arm is lower than the top of his arm, the bottom of his arm would feel more of the force, would feel more pressure forces. And so you have this net force pressing upward on objects that are submerged in liquids. And it doesn't matter if the object sinks on its own, or if it floats on its own, or if it does something in between. There's always a force pressing upward on objects that are submerged in fluids, and that includes gases and liquids. And that force is what we call the buoyant force. And the buoyant force is the thing that keeps rocks from falling through water very quickly. They kind of slowly fall through water. It's the thing that keeps boats floating on top of the water. It's the thing that keeps submarines floating in the middle of the water. It's the thing that keeps balloons floating in the sky, hot air balloons. It's the thing that makes hot air balloons rise. This buoyant force is present on every object that is submerged in a liquid that displaces that liquid at all. So what's the trick? The trick is, if you want a boat to float on top of the water, it needs to displace more fluids, more weight in fluid than the weight of the boat. If you have more weight in fluid displaced than the weight of the boat, then that buoyant force will actually lift the boat up. And that's what he discovered. So Archimedes' principle is essentially that. It is the definition of the buoyant force. The buoyant force says, the buoyant force is equal to the weight of the fluid displaced by the object. And if that is true, then we can use the things that we know so far to put an equation together for that. The weight of the fluid that is displaced is going to be equal to the volume of the fluid displaced times the density of the fluid. So it'll be volume times density. And that will be equal to our buoyant force. They don't really have an equation for that here yet, but that's the equation we will use. I'm looking for the equation here. Here they show that the buoyant force, F sub b, is equal to the weight of the fluid displaced. Here they show it the weight of the fluid displaced. But if you want to calculate the weight of a certain volume of fluid that's been displaced, then you use the volume times the density of the fluid. Right? So let's take a look at this. The buoyant force, how it depends on shape. So we have a 10,000 metric tons of solid steel that is essentially just a big block of steel, right? This is just a big solid block of steel, a square of steel, a sphere of steel, whatever. 1.0 times 10 to the 7 kilograms of steel. It's completely submerged in water, and we want to calculate the buoyant force on this 10,000 metric tons of steel. Compare us with the steel's weight. Well, how much volume is going to be displaced by this steel? The steel has a particular density, and we can calculate the volume of the steel from that density. So that's exactly what we're going to do here. The volume of the steel is going to be the mass of the steel divided by the density of the steel. So the volume of the steel is 1.28 times 10 to the 3 meters cubed, and that's how much water it will displace. And we take that volume, that's the volume of the water that will be displaced by the steel. It's the same as the volume of the steel. We take that volume and multiply it by the density of water, which is much smaller than the density of steel, and we get 1.28 times 10 to the 6 kilograms mass of the water displaced. Once we know the mass of the water displaced, we multiply that by gravity to get the weight of the water displaced, and you get 1.28 times 10 to the 6 kilograms times 9.8 meters per second squared equals 1.3 times 10 to the 7 newtons. And notice the discrepancy here. The weight of the steel is 9.8 times 10 to the 7 newtons. It's 10 times almost the weight of the water. Well, maybe 5 times the weight of the water. 6 or 7 times, whatever. 7 times the weight of the water. But it's a great deal more weight than the water. If the buoyant force is equal to the weight of the water displaced, then you have a force upward on the steel of 1.3 times 10 to the 7 newtons from the buoyancy of the water pressing upward on the steel, but you have gravity pulling downward at 9.8 times 10 to the 7 newtons. It's gonna sink. The force downward is much greater than the force upward. However, what if we change what if we change the shape of the steel into a different shape? For example, instead of being one big solid block, what if we make it into a much, much bigger hollow box that the water can't get into? So now we have a big hollow box, and they tell us that we can with this amount of steel we can displace a particular amount, a maximum amount of volume of 1 times 10 to the 5th meters cubed. So now we're displacing much more water using the same amount of steel. So the mass of the steel is still going to be the same. The force pulling downward on the steel is going to be the same, but the volume of water it's going to displace is going to be much greater. So if we have 1 times 10 to the 5th meters cubed of water being displaced, and here's the density of water, it's 1,000 kilograms per meter cubed. We multiply those together, we get 1 times 10 to the 8 kilograms is the mass of our water. To get the force, the buoyant force, we multiply that mass times gravity at 9.8 times 10 to the 8. And guess what? That is actually the same as the mass of the steel that we started with. Actually, it's 10 times greater, the weight of the steel, rather. The weight of the steel that we started with was 9.8 times 10 to the 7 newtons, but now the buoyant force pressing upward opposite the direction of the weight is 9.8 times 10 to the 8 newtons. So now we have enough force to hold up this entire boat. In fact, we have 10 times as much force as we need to hold up this boat, so we can fill this boat with some things. Some people, some cargo, whatever. And you have a buoyant force that can actually be of practical use as a boat. Oh, here they go into that equation I was talking about. So here we have a new version of Archimedes' principle that's going to include density, and they're just going through to replace weight with density times volume times gravity. It's not a great big deal, but wow, why is it that I can't go to the next page? Oh, I don't know. I think my battery is about to die. Hold on just a second. There we go. Okay, so here they actually show two different boats. One boat that's not loaded very much, so the downward weight of the boat is not so big, but the upward buoyancy force is, really big. And here, if you put more stuff in the boat, it submerges more. Well, the great thing about it is that as you submerge the boat more, you actually displace more fluid and you actually get more buoyant force. So if you have 10 times the buoyant force you need, you'll be able to add 10 times more mass before this thing is sunk to the point that it's actually underwater, right? So for our particular boat that we did in the example, we could load on probably 7, 8 times as much stuff into the boat as the mass of the boat, and still not sink the boat. And that's the beauty of shipping things overseas. These big boats can just hold just so much stuff. I was going to say a ton, but it's much more than a ton. There is no real weight limit to things that these boats can carry. I mean, in the let's see, it was 200 years ago when the Smithsonian Institute was created. The Smithsonian Institute was created by a man named William Smithson. He was English and he never ever visited America, but he donated his vast fortune to America to make museums, and that's where the Smithsonian museums come from. And one of the first museum that was made was actually made from the Smithson Castle. They actually took the castle in England and put it on a ship and brought it over here. And that was 200 years ago, well, maybe 150 years ago. That was a long time ago. They were able to do that a long time ago. Imagine what they could transport today across the ocean. Okay, now here they do define something that will become important to us, which is called the specific gravity. The specific gravity of a fluid or of anything is defined as the density of that thing divided by the density of water. So you're essentially comparing the density of whatever object you're interested in to the density of water to tell whether or not it will float. If you have a specific gravity that is less than 1, it will float. If it's much less than 1, it will float even better. But if it's greater than 1, and the greater it is, more than 1, the less it will float, the more it will sink. If it's equal to 1, then it will float in water, but it will float submerged underwater. So that's what that's the definition of specific gravity. Here you have a hydrometer, which is floating in a fluid of specific gravity of 0.87. Glass hydrometer is filled with air and weighted with lead at the bottom. And if it's a more dense fluid, it will float very high. If it's a less dense fluid, it'll float very low. And this actually measures your specific gravity of your fluid. This is used quite a bit in things like petroleum engineering and lots of things actually. So here I have a 60-kilogram woman. She floats in fresh water with 97% of her volume submerged. When her lungs are full of air, what's the average density of the woman? Well, of course, that's going to be related to this density ratio we just talked about, the specific gravity. So what's her average density? We can say the fraction submerged is equal to the density of the object over the density of the fluid, very similar to the specific gravity. And since we're in freshwater, it will be a specific gravity. So we're essentially using the 0.97 as equal to 97% as the specific gravity, and that's where that goes right there, 0.97. After we solve this thing for the density of the person, it ends up being the specific gravity of the person times the density of water, and you end up with 970 kilograms per meter cubed of density for that person, slightly less than water. And that's why most people float in water. Why do some people not float in water? Some people don't float so well. Well, some people have a much higher density structure. If you have a much higher muscle ratio in your body, muscle to fat ratio, if you have a very low fat content in your body, you will have a much lower density because fat has, you will have a much higher density because fat has a lower density than muscle. For the same amount of weight, muscle takes up less space. It is more dense, right? That's why you can be very fit and trim and be 200 pounds, but you can also be fat and chunky, kind of like me, and be 200 pounds. I have more fat than the average person on my frame. Well, probably not more than the average 41-year-old, but I have more fat than I would like to have on my frame. And if I was, in better shape, I would probably still weigh not too much less, but have a much smaller waistline. But also bone density is taken into account. A lot of people say I have big bones or dense bones, and that's why I'm so fat. Well, that's not true. Big bones don't really have anything to do with being fat. They have to do with being dense. They have to do with your weight, not how you look. Um, and this is a fact because, I mean, I know this is personally a fact. Even though I have a fairly, much bigger waist than I would like, my wrists and my ankles are not fat at all, but my bones are quite dense. I've put my body through more abuses than the average person, and I've only broken one bone, the bone in my finger that I broke when I hit my brother in the face. Um, but I've fallen out of trees and wrecked bikes multiple times, and I've gone through so many different accidents. I've been tackled pretty brutally playing football. Never ever broken anything except the one bone I broke when I hit my brother in the face. And apparently, anytime you hit somebody in the face bare knuckle, you're going to break a bone. That's what my doctor told me. So here is actually an interesting device that they use to determine the density of your body. They call it a fat tank. It determines your body density. Body density um, does not necessarily tell you exactly how much fat you have in your body, but it does help with it. I'm going to have to stop this recording and I'll continue it later. I'll put on another video and I'll talk to you later.